Okay, this is a section of the textbook without any concepts in it. You say, well, why should I watch this? And the answer is because the principles discussed here will help you with the problems. So we're going to do some examples of resistors in parallel and in series. So for this example, I've got two resistors, a 220 ohm and a 250 ohm. And we're going to have to decide whether those resistors are in series or in parallel with each other. So here's the battery. Here are the two resistors. Are they in series or in parallel? The fundamental question to ask is, do they have the same current or the same voltage? And you might say, well, whatever current is coming into this one is coming out of that one, and whatever current is coming into this one is also coming out of that one, because you can't lose charge. Therefore, those two must be in series. And you would be absolutely right. So resistors in series, the equivalent resistance is the sum of the two resistances. And 220 plus 250 is our old friend 470. So there's the equivalent resistor there. Now, this diagram is exactly the same as this diagram, except this one has a yellow rectangle around these two resistors. And we know where the battery is. It's over here. And I want to know whether these two resistors are in series or in parallel. Well, could they be in series? What does series mean? Series means that the current has to be the same through both of them. Well, whatever current is through this resistor gets split. And since these two resistors are different, you're going to have different amount of current in each of these two resistors, so they cannot possibly be in series. Are they in parallel? Well, what does it require? What's required for two resistors to be in parallel? The answer is they must have the same voltage across them. Do these guys have the same voltage? Well, yeah, actually they do. All of this region here is a highly conducting material, and the voltage doesn't change anywhere along that area that I've marked green. And all this area, marked in blue, is a highly conducting material, and the voltage doesn't change anywhere at all, or at least measurably, along this piece. Whatever the voltage is here in green, minus whatever the voltage here is here in blue, is the voltage across this resistor. But that voltage must be the same as the voltage across this resistor. Why? Because this one's bounded by green and blue, and this one's bounded by green and blue, and the difference has to give the voltage across it. So the voltages must be the same. These two resistors are in parallel. And you might have said, well, it's a little easier just to say, well, they look like they're in parallel with each other. But sometimes, with the screwy configurations that you'll see in some of the problems, that quick and dirty doesn't really work as well as doing this. Okay, so they're in parallel. Happy day. Well, how do we find the equivalent resistance for resistors in parallel? 1 over the resistor in parallel, the equivalent resistance equals 1 over R1 plus 1 over R2. And you're going to apply that to get this 130 ohms. You put 180 ohms here, 470 ohms here, and then remember after you've done this, and this one might be one that you just plug into your calculator, do 1 over this one plus 1 over that one, and you get an answer for that, and then don't forget at the end to push 1 over one more time so that you can get the equivalent resistance. So that's 130. Now, this diagram here is exactly the same as this diagram here, except that I've got a yellow rectangle around the two resistors that I'm interested in. Well, are these in series or parallel? You say, well, I think they're in series. And I say, why? And you say, because the current through them must be the same. Whatever current comes into this one comes out of that one, and comes into this one, and then out of that one. You can't lose any current along that path. So again, we're going to use this equation. Rs is R1 plus R2. 110 plus 130 is 240 ohms. So now you can actually go backwards and find out everything about every one of these resistors in the circuit. And let me show you how this is done. Now that I know the equivalent resistance here, and I know the voltage of the battery, I can find the current in this circuit. Say how? I say by saying V equals IR and solving for I. So I is V over R, and V is 24 volts, R is 240 ohms. Well, 224 over 240 is our old friend. It's 0.1. So the current in the circuit is 0.1 amps. And knowing the current in this part of the circuit, then we can ask, what's the current over here? So now we're going to go backwards, step by step through this, and figure out what everything is. What's the current in this circuit? You say, well, the current through both of these two resistors must be the same, because they're in series with each other. And would that therefore be the same as the current through this equivalent circuit? And I say, yes, it would. So the current through this one is 0.1 amps. The current through this one is also 0.1 amps. Happy day. Now we're going to go backwards to here. Well, we already know everything about this one. So we know that, I mean, this is the same as this, except for the yellow rectangle. 0.1 amps goes through this resistor. All right. Now we want to know everything about these guys. Well, that's a little hard because I've got the current through this resistor and I've got the resistance, but I don't know the voltage across this. I know that whatever the voltage is on this one has to be the same as the voltage on these two guys. But I don't know what the voltage is here. Well, we can find the voltage from V equals IR. I is 0.1 amps. R is 130 ohms. So 0.1, 1/10 of 130 is just 13 volts. So there's a voltage drop across this one of 13 volts. So, and we can also find the voltage drop across this one in the same way. We could have said the current through it times the resistance of 110. But now, knowing the voltage drop across this one, what's the voltage drop across the 470 ohm resistor? And you say, well, I know that 180 and the 470 have to have the same voltage drop across them. Would that be the same as this 13 volts that's across the equivalent resistor? And I say, yes, sir. So this one has 13 volts. This one has 13 volts. Happy day. You know everything you need to know about these two resistors. And then we can back up and we can say, well, I know the voltage across this resistor, and I know its resistance. Can I find the current through it? And the answer is absolutely yes. I is V over R. So the current through this resistor the voltage across that resistor is 13 volts. The resistance across it is 470 ohms. That'll give you the current through that resistor, whatever that number turns out to be. Pretty small, looks like. And then backing up to here, the same current here, same voltage here, so it's 13 volts. And it's whatever this ugly number is in amps for this guy. Then how would you be able to deal with this one now? It's going back to the very deepest level now. What's the current through these guys? And you say, it has to be the same as this. Why? These two are in series. They have the same current. And they have the same current as the equivalent resistor. That's how you back these things up and solve a seemingly complicated problem. A lot of other examples here. We'll let you work on some of those. Consider three resistors in the battery in the circuit shown. Which resistors, if any, are connected in parallel? Okay? Which ones are in parallel? Now this one's not as easy to see. You got a current coming out of the battery. It splits. Let's call this I2 and this I1. Then the current comes out through here, comes back in here, then I1 and I2 combine back together again. The current all the way through this branch of the circuit is the same. Come back here to this junction, and they combine again to form, and let's call this I1. This is I1. And you can say, and we're going to capture this in a fundamental concept in just a second, that I1, the current into this junction, must equal, if charge is going to be conserved, must equal the current out of the junction, which is, I'm sorry, this should have been marked I3. That's I3, this is I2, this is I1, and I1, the current into this junction, is equal to I2 plus I3, the current out of the junction. Okay. So we still haven't answered the question. Let's look at R2 and R3. Are they in series or parallel? Well, quickest answer is, are they in series? What does it mean to be in series? Current has to be the same in both of them. Are the currents the same in both of them? Not necessarily. Because if these resistances are different, the amount of current going through each one will be different. So they can't be in series. So R2 and R3, not in series. Are R2 and R3 in parallel? Well, yeah. The way to see that is to darken in all of one side of both resistors with blue. Okay, so this is a certain potential. And then darken in the other side of the resistors, all this highly conducting wire here, with red. Potential difference across R3 is blue minus red. Potential difference across R2 is blue minus red. They have the same potential difference, the same voltage? Yeah, they sure do. So R2 and R3 are in parallel. And So R2 and R3 are in parallel with each other. Okay, this is a demonstration of the power produced by light bulbs that are placed in series and in parallel. This is a demonstration of resistors in series and in parallel. What I have here is a voltage power supply. I'm going to supply about 12 volts to this half of the circuit. You see all the red wires are all interconnected with each other. So you can think of the voltage here being 12 volts. Then the current passes through all these resistors and comes to this other side of the circuit with the black wires. You can think of this being at 0 volts. These everywhere here they're connected. The voltage must be the same here as here because we're ignoring the internal resistance of these conducting wires. So what happens in between the red and the black is different light bulbs appear here. I've got through this branch of the circuit, this is a junction where different wires come together, another junction, but a branch is a path between two junctions in the circuit. We've just got one light bulb. We've got two identical light bulbs in series through this branch of the circuit. And then these parts here, we've got a current coming in here. It splits into two, comes back together again, and comes out this way. So the question is, which bulbs are going to burn the brightest? You can pause the video, make your guess. Okay, what do we see? 1, 2, 3 bulbs, A, D, and E, all burning with the same brightness. B and C are dimmer, visibly. And why is that? Shown here is a diagram of what we have here on the table, with the black markings representing all these black wires, the red markings representing all these red wires, and the various resistors denoted in green. If we're interested in the current through this bulb here, bulb A, we can write down Ohm's law, V equals I1 times R. Solve for I1, the current in this branch. R is the resistance of this resistor. So I1 then is V over R. We plug that into the power equation. Power dissipated in a resistor is I squared times R. And I'm plugging this result into here. That'll be V squared over R squared plugged into here times R, which just gives me V squared over R for the power dissipated in that bulb A. For bulb B, we're going to first have to find the current through this branch of the circuit. I'm calling that I2. And the voltage across this piece of the circuit is I2 times the equivalent resistance through this branch of the circuit. When you have two resistors that are in series with each other, the equivalent resistance is twice the resistance, or as you add up the resistances of these two resistors, they're both the same, so we get twice the resistance of either one of them as the equivalent resistance for this piece. Solving for I2, substituting it into this equation that gives the power dissipated through bulb B. So we'll substitute in I2. We have to square that. It'll be V squared over 4 times R squared. Plugging it in here with V squared over 4 R squared, we get 1/4 V squared over R. That's the power dissipated in this bulb B. We'll get exactly the same result for the power dissipated in bulb C. But what you'll notice is that the power dissipated in either one of these bulbs is only 1/4 of the power dissipated in bulb A. And you might ask, well, hang on, Dr. Edwards, this is not making sense to me because I have current coming through this resistor. Shouldn't it use up some of the current? So bulb C should be burning brighter than bulb B because this uses up some of the current, and then that current isn't available to light up bulb B that's in series. And that's not the case, and the reason is there's no way for this bulb to use up. It can't use up any current. The current that passes through this one has to pass through the other one. Otherwise, there would be a buildup of charge. Current is a charge divided by a time, and a charge divided by time passing through a wire. If it somehow used it up, it would have to go somewhere, but there's nowhere for it to go. And so the current that passes through this one must be the same as the current that passes through this one. And then you might ask, well, how come D and E are burning at the same brightness as A? And the answer there is that these are actually also connected up exactly the same way as bulb A is. Bulb D gets the full 12 volts because it's got a red wire on one side, a black wire on the other side. It gets the full 12 volts of power, and so does bulb E. If we had, and the way that we've written it here shows that there's a parallel connection between D and E. We could have just as well written this equivalently like that. The connections as shown here are exactly the same as far as parallel or series is concerned as the way that it was written before. A, D, and E all get the full voltage across them, whereas B and C only get part of the voltage and hence have dissipate less power and are less bright. Okay, just to see if we have understood what's going on here. If we have battery, parallel wiring, the brightness is going to be, these are going to be brighter. And this is in fact the type of wiring that's used in your home. So each bulb gets the full brightness of the power source. But you can't continue to add bulbs in parallel here forever, because sooner or later the total amount of current required to power all those bulbs exceeds the limits of your circuit. Consider three identical light bulbs shown in the circuit. Bulbs B and C are wired in series and are wired in parallel with bulb A. When the bulbs are connected to the batteries shown, how does the brightness of each bulb compare with the others? Bulbs B and C are equally bright, but bulb A is less bright. And that is what we saw. Oh, sorry, A is more bright. B and C are equally bright, but less bright than bulb A. So that's the answer right there.